I know a lot of people who use Git, but few who have taken the time to really understand it. Instead, they make assumptions about how it works, and when it doesn't behave in the way those assumptions suggest, they turn to Google in confusion, inevitably gravitating to explanations written by other people who have made the same incorrect assumptions, and who provide misleading analogies of how it works, ending up with a picture even less clear than when they started. Eventually, the whole thing grows to seem like magic, and in the end, they just sit at their desk, type the incomprehensible incantations they found on Stack Overflow, roll a d20, and hit enter. Then they pray that the Git gods will grant their request and not condemn them to purgatory for their lack of faith. Arthur C. Clarke, the author of 2001: A Space Odyssey, once said that any sufficiently advanced technology is indistinguishable from magic. Well, I assure you, Git isn't magic. And over the next 3 videos, we're going to clear away the smoke and mirrors, peel back the misdirection on the internet, and expose exactly how the trick works. This is an interactive presentation, and in order to get the most out of it, I highly recommend you participate at home. Before we get started, let's take a moment to get you prepared. To completely play along, you'll need a few props. First, 54 playing cards. You can make your own deck as we go, with a blank deck of playing cards or even a pack of index cards will do the job. You can also download the PDF of the cards used in this presentation, print and cut them out. There's a link below. Or you can follow the other link below to learn more about getting pre-printed decks. Second, 1 or 2 markers, preferably in different colors. And third, a stack of Post-it notes. Go ahead and hit pause and get what you need. I'll be here when you get back. During the presentation, keep your mouse on the pause button. Trying to guess how much time is needed as you play at home would only result in most users either having lots of dead space or having to pause the video anyway. So if you need to pause, need to rewind, or just get sick of hearing my voice and need a break, take as much time as you need. I'm going to sum Git up in a single sentence. Please don't turn this off after hearing this. I promise that if you play the at-home version of the game, by the time we're done, you'll understand every concept in the next sentence. Git is a version control system designed to track the history of text files across multiple distributed instances without the need for constant communication between instances, by representing files, their relationships, and their history as complete raw data blobs stored in a compressed database indexed by statistically unique, content-based pseudorandom hashes, and whose entire history and content can be accessed from any arbitrary starting point by means of the recursive traversal of its node space, which is best represented in the form of a directed acyclic graph mapped, along with its contents, in 4 dimensions. The earliest version control systems were a necessary step, but were so primitive that they can barely be considered in the same family as more modern systems. They allowed tracking of files on only one computer, and often only one file at a time. Each generation eventually had a system come out on top, to the point that it essentially defined the generation. The first generation of modern version control was the Concurrent Versioning System, or CVS. It was server-based, which made it a tool that could be used by teams, but major features like branching were very difficult to do, and as a result, usually were ignored altogether. Mostly because people were fed up with using CVS, Subversion was created as a replacement. Billed as CVS done right, it was largely modeled after CVS in how it did things. For example, both systems were centralized on a server, and without an active network connection, it was impossible to commit. While easier, branching was still expensive, somewhat difficult to manage, and problematic to merge. Again, most teams just didn't want to deal with it and developed on a single branch. The current generation of version control went back to the drawing board and attempted to build a more modern system that would work for the new realities of development. Git and Mercurial are the 2 open source systems in this generation, and while they function very differently in their specifics, they are, in fact, very similar in their operation. Both are distributed systems, so while there can be a centralized server, repositories are cloned locally, and users can interact with them without the need for an active network connection. This fact alone makes this generation much better suited for the work-anywhere nature of the modern development team. Git was released in 2005. It was originally written by Linus Torvalds to manage the Linux kernel project. Even after 10 years of use, Git still seems to be very confusing for a lot of people, and there are several reasons. First, people who understand how it works tend to use a lot of fancy computer science-y terms when talking about it. And while they are accurate, it really only means something if you already know what those terms mean. Things like directed acyclic graph and recursive traversal of the node space. It's also very difficult to diagram a Git repo in a way that isn't misleading. There is a lot of incorrect information about Git floating around. Most of it is relatively harmless and won't hurt you in learning how to use Git, but in order to really leverage Git, you need to understand how it thinks. Its distributed structure takes some getting used to, especially when you're used to older centralized systems. A lot of misinformation and difficulty comes from trying to compare Git to systems you already know. A lot of the commands are similar to older systems, so many people incorrectly apply their understanding of CVS or Subversion to Git, which will eventually cause them headaches. Because of its distributed nature, you'll frequently have multiple versions of the same branch, one referencing your state and others representing the state of the branch on copies of the repo in other locations. A very legitimate difficulty with Git is that it tends to value speed over ease of use, and as a result, the command line syntax can often be, a little wobbly. But as you learn how Git works, a lot of it will make more sense. Every object in Git is given a hash to identify it in the database. Git uses a SHA-1 hash. It generates the hash based on the contents of the file. SHA is a waterfall hash, so a single bit changed anywhere in the file drastically alters the final hash. The hashes produced follow no known patterns, even though they are based on content. Hashes are statistically unique, meaning that the probability of the same hash being generated for two files is so astronomical that it isn't even worth considering. SHA-1 produces a 160-bit hash, meaning that there are 2 to the 160 possible hashes. That's big. Really big. Imagine we were to write each hash value on a standard poker-sized playing card. It's hard to express how big that is, but we'll try. Our galaxy is 100,000 light-years across and a little over 1,000 light-years thick. A light-year is a little under 6 billion miles or a little under 9.5 billion kilometers. Our imaginary deck would cover the entire galactic disk and be stacked over 4,000 light-years high. This deck of cards would require the matter over 1 million Milky Way-sized galaxies to manufacture, and it would promptly collapse into a black hole that would wipe out all life. For simplicity and safety, we've compressed the hash space for this presentation into a normal 54-card deck. So grab your deck and your markers. We're going to build a Git repo that exists in the real world, made out of familiar objects that you can hold in your hands and manipulate on the table in front of you, instead of in some abstract virtual space.